In the present discussion, we have to talk about Wiedemaan Franz law. The ratio of thermal to electrical conductivity of all metals is a constant, and the ratio is proportional to its absolute temperature, which is our Wiedemaan Franz law. Here K is a thermal conductivity, sigma the electrical conductivity. K by sigma is proportional to T, absolute temperature. In order to remove the proportionality sign, we are introducing a constant L, which is called as Lorentz number. K by sigma T equal to the Lorentz number L. Now we have to derive first the thermal conductivity value and the electrical conductivity. Finally, we will arrive the K by sigma ratio. Now we will do one by one. Now we have to derive an expression for thermal conductivity. Generally, heat is conducted in solids either by the electrons or by the lattice vibrations. In metals, conduction by free electrons dominate. Consider a conductor with unit area of cross section. One end is kept at a higher temperature than the other end. There are three sections A, B and C separated by a distance lambda, the mean free path, will be at different temperatures as shown in figure. See, this B is at a temperature T, A is at a temperature of T plus dt by dx into lambda, whereas C is at a temperature of T minus dt by dx into lambda. Now we have to consider the net heat transfer and net energy transfer across B. It is a known fact that 1/6 of the total number of electrons move from left to right, and similarly an equal number move from right to left, and they contribute to energy transfer. On the basis of energy momentum, 6-dimensional space, we have made our assumption that only 1/6 of the total number of electrons move from left to right, and similarly an equal number move from right to left, and they contribute to the energy transfer. The amount of energy transferred from A to B, the amount of energy transfer from A to B equal to 1/6 NV, then d by dx into lambda. In the same manner, the amount of energy transfer from B to C, which is equal to minus 1/6 NV d by dx into lambda. Here n stands for the total number of electrons, V the velocity of the electron. Now net energy transfer across B, net energy transfer across B, which is equal to 1/6 NV dE by dx into lambda minus of minus 1 by 6 NV dE by dx into lambda. Minus and minus plus 2 times 1 by 6 NV dE by dx into lambda, which is equal to 1 by 3 NV dE by dx into lambda. The net transfer of energy across B, which is equal to 1 by 3 NV dE by dx into lambda, which is equal to heat transfer. The net energy transfer across B is equal to heat transfer Q. Q equal to K into dt by dx, where K is our thermal conductivity. This is our thermal conductivity. K into dt by dx, which is equal to 1 by 3 NV lambda into dE by dx. This net energy transfer is equal to our heat transfer. K into dt by dx, which is equal to 1 by 3 NV lambda into dE by dt into dt by dx. This dE by dx is modified as dE by dt into dt by dx. Now we can cancel dt by dt by dx. Then K equal to 1 by 3 NV lambda into dE by dt. But dE by dt is our specific capacity at constant volume. This is equal to 1 by 3 NV lambda into CV, where CV is equal to dE by dt, specific capacity at constant volume. Now, according to kinetic theory of gases, half mv square, which is equal to 3 by 2 into kb into t. From this, the value of V equal to 3 kb into t divided by m inside the root. This is the value of B. Furthermore, you may write the value of CV also. The value of CV equal to d by dt. Say this is E. E equal to half mv square equal to 3 by 2 into kbt. From this, V equal to 3 kb into t divided by m. Then find out the value of d by dt. From this equation, dE by dt, which is equal to 3 by 2 into kb. Now in this expression, we have to substitute the value of V and d by dt to get the value of k. Take this equation, k equal to 1 by 3 n lambda, then the value of b is 3 k suffix b into t divided by m inside the root. This is multiplied by d by dt. The value of d by dt is 3 by 2 into k suffix b, which is equal to 1 by 2 n lambda kb into 3 kb t whole divided by m, k suffix b into t. This is the value of thermal conductivity k. 3 cancelled, 1 by 2 n lambda into kb multiplied by root of 3 k suffix b into t whole divided by m. This is the value of k. Now you have to find out the value of sigma, electrical conductivity. Then we may come to the final part, kb sigma. When an electric field is applied to a metal, then there will be a flow of current I in the direction of the electric field with current density J. Current density J is nothing but I by A. The value of current density is equal to sigma into E. Here sigma is our electrical conductivity. But the current density depends upon the number of electrons, charge of the electron, and the velocity of the electron. J, which is equal to n, the number of electron, charge minus E into E. J equal to minus n E into B. Suppose an electric field is applied to a metal, the force acting on the electron, equal to minus E into E. According to Newton's law, F is equal to ma, mass into acceleration. Suppose m be the mass of the electron, then acceleration is rate of change of velocity dvd by dt, which is equal to minus E into E. From this dvd by dt, which is equal to minus E capital E divided by m. This is our acceleration. Acceleration gained by the electron. From this you may find out the velocity v suffix d. If you integrate this, you can get our d. dvd, which is equal to minus E capital E divided by m into dt. So if you integrate this, actually this is dvd, this is minus E capital E divided by m into dt. Then the drift velocity equal to minus E capital E divided by small m into t. This is our collision time. V suffix d is our drift velocity. Now the current density J becomes J equal to minus n E. This is the value of E, V velocity, minus E divided by m into t, collision time. Minus into minus plus n E square capital E divided by m into tau. Now sigma, that is electrical conductivity, is J by E. Sigma, which is equal to J by E, which is n E square divided by m into collision time tau. Now we'll simplify this equation further. The average distance traveled by the electron in time t, that is collision time, is lambda. Here lambda is the mean free path. You know that velocity equal to distance by time, which is equal to lambda divided by tau. Instead of this time, we can write lambda divided by v. So in this expression, we may write sigma, which is equal to n E square divided by m into lambda divided by v. from the kinetic theory, half mv square equal to 3 by 2 into kbt. Kb is the Boltzmann constant. From this, V equal to 3 kb into T by m. Now substitute this value in the above expression. Sigma, which is equal to n e square by m into lambda divided by this V. It is root 10 divided by 3 kb into T inside the root. This is the value of sigma. Now come to our Wiedemaan Franz law. K by sigma. We will provide the Wiedemaan Franz law. K is our thermal conductivity, sigma is the electrical conductivity. Now we have to substitute the value of K. K is 1 by 2 n lambda K suffix b 3 K suffix b into T by m inside root. This is the value of K divided by sigma. Just we have to put this 3 kb into T by m. See this factor. Then 1 by lambda m divided by n e square, which is equal to 1 by 2 this see here this n cancelled out, this lambda cancelled out, write on this kb 3 kb into T divided by m without root. Then this m into m cancelled out, so we make it 3 kbt alone. Root m into root m cancel. This is equal here 1 e square is present, kb by e square. Verify 1 by 2, this n get cancelled, this lambda get cancelled, root m into root m is m get cancelled, root of 3 kbt into root of 3 kbt is 3 kbt. Already one kb is present, we have taken out this e square outside. Now this is equal to 3 by 2 kb into kb square divided by e square into T. Then this is modified as k by sigma, which is equal to 3 by 2 k suffix b divided by e whole square into T. This is k by sigma, which is equal to L into T, where L is our Lorentz number, which is equal to 3 by 2 kb by E whole square. Now we have arrived at the Wiedemaan Franz law. The ratio of thermal to electrical conductivity of all metals is a constant and is proportional to its absolute temperature.